Okay, so we are actually recording this, and I request every speakers for this tutorial record their lecture and upload to the YouTube, our YouTube channel. Okay, so if you follow YouTube link and search for this UNIST Vision and Learning Laboratory, then there's a YouTube channel for our lab. Okay, and also you can take computer vision class that I lecture. We always upload our lecture there, so you can I mean see the video there for the lecture, and also we upload also the every week's seminar, the paper seminar in the YouTube channel, so you can also see the video for that. And also we will also upload this tutorial session to share that to newcomers. Okay. So today I would like to introduce this MANO and SMPL models, which is very essential for our research, and wanting to show some of the use cases of that in especially in 3D pose estimation, and wanting to introduce our lab's research for last 5 years. Okay, so this SMPL, which is the abbreviation for Skinned Multi-Person Linear Model, is actually introduced in TOG, which is the good journal paper in graphics domain. And this Michael Black, this guy is very famous. This is the professor in MPI, Max Planck Institute, and it is becoming he's becoming very famous. And due to this, I mean, 3D model, okay. And this SMPL is representing the human body 3D meshes, especially they can represent human body as a mesh. At the same time, we can control humans' pose and shapes via this SMPL model. So that's two important things to understand. Before that, I want to introduce what is mesh. Okay, so the left is the mesh representation. Okay, so we first need some vertex. Okay, in Korean is 꼭지점. This is the vertex point. Okay, so vertex for representing vertex, we need to write their XYZ coordinate. So we always need 3D representation for each vertex point. Okay, and also there are face. Okay, so by connecting three vertices, we can define one face. We normally call that as triangular face, okay? Because there are 3 points that's triangle, so we call that as triangular face. So mesh is composed of face and vertex, okay? And normally in PC, in computer, we save the 3D mesh in the OBJ format. That's actually file format, okay? And if you read the OBJ file, then their format is looks like this. So they first define each vertex, okay? And for each line, they define their XYZ coordinate. Okay, so this is the first vertex, second vertex, third vertex, and so on. So we first define each vertex their 3D XYZ coordinate. Okay, and then we next define the triangular face. Okay, by connecting three indices of vertices. Okay, so actually, this format is indeed saying that mesh, when describing a certain mesh, we need vertex and faces. And vertex is composed of XYZ coordinate, and face that is composed of indices of vertices. Three vertices compose the face. Okay, this is the mesh representation. And but I mean, when given this mesh, they are somehow static. We cannot control this rabbit change their pose or change their shape easily. It is not trivial in this format. Okay, if we change the value of vertex, then abruptly this vertex change into some coordinate in the 3D space. So changing the vertices systematically to change these rabbit's pose and shapes is not trivial. Okay, it's not easy. Okay, but this SMPL mesh is providing the 3D mesh representation of the human. At the same time, it can give us the capability to control these human meshes pose. So at the initial stage, the humans are in T pose. Okay, we call this as the canonical pose, or some which is meaning some basic pose. Okay, some mean pose. We call that as canonical pose or just T pose because their shape is T. Okay, or sometimes we use A pose. Okay, by down. I mean two hands are down like this, then we call that as A pose. Okay, that's popular mean poses. Okay. Anyways, from the T pose, which is the mean pose, we want to control the human's pose into some pose that we know. Okay, and also this person's shape. We also can change this person's shape into others. Okay. That's what SMPL model wanting to achieve. Okay. So we can call this n as the function, and we will call this beta as the shape parameters of the SMPL, and zeta as the pose parameters of the SMPL. Okay. So if we input shape parameter and pose parameter, this n is the function that can map these parameters to the as a 3D mesh representation. In SMPL mesh, there are over 6,800 vertices predefined in the 3D space. So in this mesh, we have 6,800. I don't remember the exact number. Anyways, 6,800 number of vertices on here about that. And also by connecting the vertices that 6,000 number of vertices, by connecting three vertices, we can define triangular faces. Okay. And there are over 15,000 faces in this SMPL model. Okay. Okay. Now I will introduce how SMPL models have been built and wanting to explain how these kind of things can be achieved in SMPL model. Okay, so here you can see the data sets having multiple shapes. Okay, so here almost over 30 humans shapes. Okay, and their pose in A pose. Okay. We can regard their pose as same, but only the shape parameters are different. Okay. And here we have the pose data, multi-pose data for the same person. Here the shapes are same, but their pose is different. Okay. So when constructing this type of SMPL mesh, we need training, and using this type of multi-shape and multi-pose data, we build SMPL model. Okay. And first, what they did for building the shape model, we first have to understand the PCA. I guess most of the graduate students they understand how this PCA is working, but maybe for undergraduate student, it is not trivial to understand this. So I want to briefly deliver what PCA is. Okay. So, I mean, these blue point are some data samples. Okay. So each point is now denoting three-dimensional some vector. Okay. We can visualize them in the 3D space. Okay. Or even higher dimensional feature, we can distribute them in that n-dimensional space in this way. Okay, I mean humans cannot understand their visualization for high-dimensional features, but I mean, anyways, they can be visualized in that high-dimensional space, right? And what PCA principal component analysis they wanting to achieve is they want to select the axis, new axis that can represent data efficiently, which means they first pick the axis that have the largest variance. So seeing the distribution of the data features among the n-dimensional n-axes, they select the one that have the largest variance, right? And then they select the second axis that is having the next largest variance, and at the same time orthogonal to previous axes. Okay, are you guys following this? If you do that, after doing several iterations for selecting the axis, you can select few axes, for example, 5 axes, but you can realize that because those axes are already very optimal for that data distribution, so you don't need n axes. Okay, rather than having n axes, you can select just few axes that is well representing data distribution. Okay, so that is the power of the PCA. Okay, and what they did for the shape space was given this type of same post multi-human data, they represent it in their n-dimensional space. For example, I mean, this is the SMPL mesh. So they somehow pre-process those meshes are having the same number of vertices. I mean, they are obtained by scanning real humans bodies using the 3D scanner. They collect this type of multi-persons same shaped meshes, okay, using 3D scanner, and they pre-process this to have the same number of vertices on the surfaces, okay. And also for the same, they also define the faces, but here you have to feel that the vertices are more important information here, okay. Uh, okay. And they represent their vertex point. All of the vertex point in the n-dimensional space, n is now the number of vertices. And then they apply the PCA. Okay. And here originally they are mapped to n-dimensional space. N is the number of vertices, which is almost 6,000. But you can pick the axis, you can pick the axis that can well represent this vertex, this mesh data, okay? And you can pick actually 10 axes that can well represent this shape variant, okay? Are you guys understanding this? And actually, when picking these 10 axis, that axis is also representing one SMPL mesh. Okay, their basis vector is also the vector in n-dimensional space, and that vector is also representing one mesh. Okay, And by linear summing that basis vectors, you can represent some new meshes. Are you guys understanding this? Okay. So this Sn is representing the basis, that axis vector, right? That is representing some of the shape meshes. That is representing some of the, how to say, uh, I mean, some of the shapes where most of the humans are sharing in the data set, right? And by linear combining those 10 mean shapes, you can represent by just adjusting this single scalar value for 10 bases, you can make the new shapes easily. Okay, are you guys understanding this? So this is what happened for controlling, I mean, the shape parameters of the SMPL mesh. So in the SMPL mesh, they are providing this SN, okay? This SN is combining this 10 SN, they are called that as large S, and this is the shape blend shape, okay? By linear combining these shape blend shapes, you can create new person's shape. And you can control the person's shape by adjusting this scalar value, right? Okay. So you can control mesh's shape, okay, by adjusting this beta. Okay, and this beta is now called as shape parameters. Okay. And also, the SMPL is providing the joint regressor, which means given, so here you are seeing 6,800 vertices on the SMPL mesh surface, and these points are meaning the joint. Okay? So in human body, we already know this is head, this is left hand, right hand, and torso, neck, and knee, foot. Okay, so that 23 point, which is very how to say essential for, I mean, pointing out the human's body part. Okay, we define key point, which is sometimes called as joint. Okay, key joint. Okay, so here this is elbow, maybe this is left hand, wrist. Okay, head. This type of point, we already define some joint. Okay, so how to say, connecting the relationship between joint and SMPL mesh, which is 6,800. Okay, their vertices, but the relationship between vertice and joint. Okay, we want to somehow wanting to know that. Okay, so SMPL provide, they explicitly train this joint regressor that can map joint their locations uh, from the SMPL vertices. So for example, when getting this joint, they are getting weight from nearby SMPL vertices. Okay, and for getting this joint, they are regressing their position by knowing the surrounding SMPL vertices in here. Okay, so when knowing SMPL vertices, you can directly estimate the joint locations as well using this joint regressor. Are you guys understanding this? Okay. So SMPL already trained this joint regressor, and their dimension might be 6,000 times joint number. Okay, they are having some weight for each joint from the SMPL vertices. Okay, and their weight sum is one by summing the SMPL contributions. Okay, so this is the joint regressor we can use. And next important thing is the pose, okay, we already know now we can control the SMPL meshes, their shapes, okay. Given this beta, we can, by manipulating this beta, their weight, their axis weight, we can control humans' shapes, okay. But next thing is how to control the pose, okay. So here, this is showing adding some, this T bar means the mean shape of the human. And by adding B of S, which is the shape blend, we learned this here. This is the shape blend, which is the linear summing of shape blends. By adding this T plus BS, we can manipulate their shapes, but they are still in the mean pose, okay? Their shapes are becoming different from the initial one, but their pose is still not changed. So from here to here, we want to manipulate these meshes in the pose aspect. And what we will do that is, we actually have the angles, we predefine the angles for each joint, okay? So there are actually 23 joints on this mesh, okay? And we define 3 times joint number of angles, okay? So, which means for each joint, we can define 3 angles that can rotate that joint, okay? And if we can multiply the rotation matrix for this joint and some vertices that is related to this joint, then this part will be rotated respect to that joint. Okay, are you guys understanding this? So mathematically, moving the arm is multiply rotation matrix to the vertices related to that, I have to say elbow joint. Okay. So by doing the similar matrix multiplication for all the joints, we can manipulate their pose. Okay. And here we actually have that kind of thing here. So zeta is defined as the rotation angles. Okay. Three-dimensional rotation. There are K means the joint number, 23 actually. And each omega 0, that is beta, and having 3 angles. Okay. So this omega is having the rotation XYZ rotation angles, 3-dimensional rotation angles for K joint. Okay, and that is actually pose parameter of the SMPL. Are you guys understanding this? And actually, there are sector, their dimension is 3 times 23 plus 3 because this is the omega, their dimension. And we need this one more 3-dimensional rotational angle because we were also wanting to rotate the SMPL itself globally. So this 3 is the rotation angle for global rotations. So pose, we have 72 parameters. Okay. And also, mathematically, using this Rodriguez formula, we can make it into some matrix. That is only 3-dimensional vector at the initial time, specifying the rotation angles itself. But using this formula, we can make them into the rotational matrix, which is 3 by 3 matrix. Okay. And then using this formula, first we make the G of K, okay, which is the, I mean, this is same matrix, 3 by 3 rotational angle, and also counting into their translation, we made 4 by 4 matrix. This is a normal geometric transformation matrix, Okay, are you guys understanding this? Okay, and we actually accumulate that for A of K, which means there are some kinematic tree in the human bodies. So, for example, when rotating this, wrist, we also have to count arm rotations. Are you guys understanding this? We rotate this wrist, right? But if we rotate arm as well, the wrist, their angles are also affected, right? Are you guys understanding this? So when getting the position of the hand, we also have to count, we don't have to count merely the rotation of the wrist, but have to count rotation of the arm as well, right? So there's actually kinematic tree in the human body part, right? And this A of K is meaning that kind of kinematic tree, okay? For rotating wrist, we have to count the arm because that's the parent of the wrist, okay? And also leg is also same, having some kinematic tree. So this A of K, this SMPL is defining that uh, considering the structure of the humans already, okay? So for that kinematic tree, they multiply this matrix, okay? And that is becoming this G of K, right? And also, we also have to make them into G prime K by reducing the, how to say, influence of the mean pose. Okay, so I said A pose or T pose, that's the mean pose, right? But we have this sector star is meaning that mean pose. Okay, we are wanting to eliminate the influence of that mean pose, that initial pose. So we multiply the inverse of that mean pose and multiply the new pose, their transformation matrix. Okay. And now G prime K, that becomes the transformation matrix for each vertex. No, not each vertex, but each joint. This K, G of K, that is obtained for each joint. Okay. And now this Ti is meaning the vertices on SMPL. There are 6,800 vertices on SMPL. So this I, there are that number of I index here. And Ti means each vertex on SMPL mesh. Okay, are you guys understanding this? And they are multiplied with G prime K we just calculated. Okay. And this WK comma I is uh, including actually that W is meaning this. Okay. How to say, I mean, um, this color coding is actually showing this W blend weight. We call that as blend weight. And that at each entry of this W matrix is called this as Wi, comma K, which means each vertices of this SMPL mesh, each vertices can be mapped to K disjoint part. Okay, so and each color is denoting that. Are you guys understanding this? So there are K part in human body. Actually, we define it as 23 part. And here, SMPL is having 6,800 vertices. So we can map each vertex into one of 23 part. Okay. And that weight we visualize here, and that is showing this W. Are you guys understanding this? Any questions? No? Okay. 이거 6,890개 꼭지점을 23개 파트로 매핑한 다음에 색깔로 나타내면 이렇게 된다. 색깔은 의미 없고. 알죠? So this WKI is the entry of that blend weight, W. Okay, and G of K, that is the transformation matrix of the each part. Okay, and TI means each vertex on the SMPL. So by multiplying these three, this G of K is the transformation matrix for each part, 23 part. But we know the way, the relationship between part and SMPL vertex by using this weight, blend weight. And this TI is the vertex in SMPL. Okay, so and by multiplying these three and summing over all the part, we can we can get new vertices position. So this is how each vertices of SMPL mesh is transformed based on the pose parameter setup. Are you guys understanding this? Okay. And the other thing is, I mean, this pose, no, this blend skinning, this is called as blend skinning because we are only having the pose their angles. I mean, this sector is actually similar to the skeleton information, which has the joint information only. But via this process, we can control the whole meshes. So this is similar to, I mean, wrapping some skin on the skeletons. So we call that as blend skinning. And blend shape that is controlling the shape, okay? And after that, this is the last part. But without this, already we can control the shape of the person. And also we can control of the mesh already, okay? So as I mentioned previously, we already know about this beta, which is the PCA coefficients, and zeta is the angles of the joint. Given these two, we already can manipulate the person's shape and also their poses, okay? But remaining thing is this transformation. Actually, there are slightly their person's shape is becoming different for especially for these regions. Are you guys seeing that? Right? And that part is called as post blend shade, which add this BOP one time. Okay, that is actually I mean obtained via this how to say via this formula. Okay, and they are only parameterized by this sector parameter, not by the beta. They are parameterized by the sector. Okay. Even though their, I mean, variation is very small, but this post-blend shape is considered because they wanting to model some muscle bulging or joint volume things. Okay, so anyways, they just want to finely model nonlinear surface deformation due to some muscle movement. So that is actually reflected in the shape model like this. So because of that, they are not depend on is controlled by this beta, which is the shape parameter, but by the pose parameter sector. Okay, they wanting to further counting this pose, some of the shape variation due to the pose. Okay, and previously in previous there are actually 3D models before the SMPL. Previous models are modeling this using some nonlinear, because that deformation is nonlinear in nature. They did that using the nonlinear formulation, but in SMPL, they formulated as the linear formulation, but this is anyways the approximation. Okay, so and also their effect is very small. And more important thing is to understand this pose variation and this shape variation. Okay, are you guys understanding SMPL now? Okay, so when we call SMPL, it has these 5 parameters. They are already learned by SMPL authors. So T means the mean shape, and W means the blend weight, which have the relationship between weight and the vertices to the each part. And S is the axis for the shape, and J means the joint regressor, and P is the post-blend shapes, which have minor effect. Okay, so these 5 is defining the SMPL model. Okay. So is it impossible for us to model that same without live maybe, yeah. Yeah. Maybe that's the limitation yeah, for this. Okay. And W is visualized here. The blend weight are visualized here, and the joint regressor is also visualized here. Okay. And using these pre-trained parameters, we can manipulate the meshes, SMPL meshes, given conditioned on this shape and sector pose parameters. Okay, that's the SMPL. Okay, and that was actually the hardest part in this lecture. Okay, and MANO is the paper also published in SIGGRAPH and TOG in 2017. And this is also published by the same group. Okay. And initially, their motivation was modeling hand and bodies together. Okay. Previously, hands models are, SMPL already have the hand, but because hand is very small part of the human body, so their error was minor when fitting the 3D meshes to the image. Hand easily ignored. And also SMPLs, they have just one joint for the hand, right? So they only count their rough rotations, okay, but not their fingers configurations before in SMPL. So to deal with that, MANO has been proposed. Uh, for one of these laws showing the result fitted via the SMPL, and the other one is MANO, SMPL plus MANO. Okay, so they initially wanting to achieve hand body fitting together by attaching MANO model to the SMPL. They want to fit the 3D they want to control the 3D models in the aspect of hand and body together. But nowadays in hand, somehow hand reconstruction and body reconstruction, they are becoming separate because hand, even though it is very small part of the human body, but we normally use hand to achieve many things in daily life. Okay, even though it is small part, hand is also exhibiting many degrees of freedom to control. So hand is becoming the independent research topic. So nowadays, MANO is separated from maybe differently to original intent. MANO is becoming separated from the SMPL model in many cases. And so I also wanting to anyways explain this MANO model, but basically because it is coming from the same group, they are sharing the same blend shape and shape blend shapes and pose blend shapes. So their formulation is actually same. So they are building this mean shapes, mean axes, samely as SMPL. but using the different data, hand data, and build these blend shapes. And also, they also build the blend skinning method. Okay, but one difference was because human hand, their fingers are how to say showing high degree of freedom. They first initially they apply the PCA on the pose domain as well in MANO. Okay, I mean in the SMPL, you may remember that pose parameters are axis angles, the rotation angles. But in MANO, because their degrees of freedoms are high, initial MANO, they apply the PCA on that rotational angles. But this PCA cannot represent all of the angles, right? Because without using all the bases, PCA is not same as the original space. So PCA can lose some information. So nowadays, many people are using the same actually uh, pose parameters as the SMPL, not using the PCA in many cases. But the implementation wise is very simple, just removing the PCA and using the low rotational angles. Okay. Anyways, you can roughly think MANO is same as SMPL. Their formulation is same as SMPL. We can control the hand meshes based on the pose and shape parameters. Okay. And in the year of 2016, uh, at this time, deep learning was not that popular. I mean, deep learning first appeared in 2012. And after that, many deep learning architectures are coming. But at this time, this SMPL model was not used in the deep learning pipeline. And this is the work that wanting to fit this SMPL model to the pose of the images. Okay. But actually, there was not much tools to map these images into this SMPL model. And what they did in this paper was they first infer the human skeletons by training the deep learning network that can regress this XY 2D coordinate. Okay. So in the year of 2016, there was some of deep learning CNN-based approaches that can map this RGB image into this type of 2D floating values, okay, 2D skeletons. There, I have to say, there are one, two, maybe 20, about 20 joint defined, and we can, how to say, define their XY point coordinate. Okay, so there are about 40 floating values, and from the RGB image, we can, by training the regression network, we can infer these 40-dimensional floating values. Okay, and then what they did was this SMPL mesh, we can infer the joint, okay, via the joint regressor, we can get 3D skeleton from these 3D meshes. And then we can also, that part is actually looked here, okay? So this J means the the joint regressor, okay? So from here, and also, I don't know the exact formulation. Maybe this is for pose skinning. I think this is the shape blending, and this might be the pose skinning. Okay, for this we can, by doing this we can have the posed meshes, and then we can project that into the 2D space. This is the differentiable. Originally, the camera rendering process is not differentiable. Uh, cannot be computed exactly, but they approximate the 3D to 2D projection. So they project the 3D skeletons in the 3D space into the 2D space via this operation. Okay. They are multiplying some of the intrinsic camera parameters to these 3D skeletons. There are multiplication, basically. And anyways, this is mapped to, I'm not sure about this law function, but because I'm not familiar with this paper, but I just want to deliver some messages to here. So this becomes the 2D skeletons coming from the SMPL model. Okay, are you guys understanding this? So this is the how to say 2D skeleton differentially calculated from the original 3D mesh, and this is the 2D joint coming from this another separate deep learning architecture. So we can regard this JEST as the constant 2D skeleton, and wanting to optimize sector and beta to make these 2D skeleton coming from the SMPL becoming similar to this 2D joint. Okay, are you guys understanding this? So they are not training any network, but apply direct optimization for sector and beta by minimizing this objective. So I mean this is EJ, which is the main objective, and some others are some regularizers. So by minimizing this energy term, they are finding the optimal beta and sector that is well matched to the 2D joint estimated from the RGB image. Okay, that was the original approach that wanting to fit SMPL to the RGB image. Okay. But this paper appeared in CVPR 2018 and recorded as HMR frequently. Okay. This paper was actually the first to apply to motivated to apply this SMPL mesh in the pipeline of the deep learning. Okay. So you already know about this process. So this mesh, SMPL mesh, can be controlled by these pose and beta parameters, shape parameters, and they can be mapped to the skeletons via the joint regressor, and they can be also approximately projected to the 2D joint by multiplying some intrinsic parameters. Okay? And this becomes the 2D joint estimated from the differentiably calculated from the 3D mesh. And this X is meaning the ground truth to these skeletons. Okay? And when reading this paper, CVPR 2018, please omit this part. It is not helpful for understanding the entire paper. So I will delete this part and explain about the remaining things. Okay. And so this is the SMPL and projection and the loss function we mainly use. Okay. And the network, when training the deep learning, we need to get some parameters of the network. Okay? We optimize the parameters of the network. And we actually wanting to get these 5 intermediate parameters from the RGB image I and wanting to train this network to properly estimate this SRT, beta, and sector. Beta and sector is the shape and pose parameter, respectively, right? So we already know about this. So we are wanting to want this CNN architecture estimate proper beta, which is the shape and pose parameters for this RGB image. Okay? And using that beta and sector, we map it to 3D mesh and map it to skeleton and project it to the 2D skeleton and getting loss to make it similar to the 2D skeletons, which is the ground truth. And to get the feedback from this loss, these network parameters are learned. Are you guys understanding this? This is the HMR, their idea. And what is SRT is, so this X sector beta, that is representing the 3D skeleton. And by applying some global rotations for this 3D skeleton, we can, I don't know, but SMPLs, they cannot represent some people who is lying, okay? So they cannot easily representing the person who is lying. So that can be trivially denoted by multiplying some global rotation matrix to the entire skeleton. So this R is representing the global rotation of the SMPL mesh, their skeletons. And this pi is again representing the 2D projections, okay? And then we will multiply some of the scales to the obtained 2D skeletons, and we'll add some translation vector to that to, how to say, uh, make the proper scaled 2D skeletons that is comparable to this ground truth 2D skeletons. So anyways, this X, which is the final output of this network, is how to say, in formula, we can write their formulation. So which means from vector and sector and SRT, all of the remaining part is differentiable. Okay, so we are getting because and also this part is CNN. So from the I to this X hat, all of the components are differentiable. So we can train that using the loss, final loss. Okay. So that's actually what this HMR does. Okay, are you guys understanding this? And also, from now on, maybe most of the contents are explaining about our research, what we have done using this how to say HMR and SMPL and MANO. So actually, I did these things in 2019. And actually, you can roughly think I made some deep learning architecture that is similar for the hand domain. Okay. HMR is using SMPL, wanting to mapping the image I to the mesh. Okay. And this paper is doing the same in the hand domain. So input image, that is hand RGB image, and wanting using the MANO model, we map it to 3D mesh, okay, using only the 2D skeleton and mask supervisions without any 3D mesh supervision. And in the middle, we also add some of the 2D pose estimator and also the component that is counting for these 2D masks, okay. Anyways, basically they are similar to what HMR does. Okay? They are estimating SRT, which is the scale parameter, rotation parameter, translation parameter, and sector and beta, which are shape and pose parameters of the MANO, and make this MANO mesh intermediately and map it to the skeleton, project it to the 2D space, and multiply, scale, and translate it, and compare with the ground truth 2D skeletons. Okay, and by doing that, we can train these earlier networks that estimate SRT and sector and beta. Okay, are you guys understanding this? So 3D hand pose or 3D pose estimation is roughly we can say that they are doing the regression task. Okay, so from the RGB image, this is the input of our system, and 3D representation could be either 3D skeleton or the 3D mesh. Okay. So previously, before the MANO or SMPL, we normally do the 3D pose estimation using the this type of skeleton representation. In human body, there are about 20 joints predefined. And for the hand, there are 21 joint predefined. Because there are 5 fingers, 4 points are defined for example, here 4 points are defined for one finger. And because we have 5 fingers, there are already 20 joints. And 1 point is defined in the wrist. Okay. So because of that, there are 21 key points defined. So when doing the key point estimation, we normally map this FE function, which is the CNN-based regressor, inputting this input image to that deep learning architecture, and we are enforcing their output close to the 3D skeletons, okay, using the Euclidean distance, okay, summing over all the samples, we train this. So this is the normal way of achieving the 3D skeleton estimation, pose estimation. But after MANO comes, we are using this type of pipeline to map RGB images to the 3D meshes, the MANO model's parameters. Okay. And this is the demo from my, this is the demo from my CVPR 18 work. And previously we did 3D pose estimation using the depth image. Okay. Because depth image that already contains some Z component, which is a depth information. So it is actually easier to achieve this 3D pose estimation from the input with depth information. Some of the depth information, it is easy to map them to the 3D information. But we are not carrying our depth camera in our pocket, right? So, but we are carrying the RGB camera in our pocket, right? A smartphone, they are having the RGB camera. So the research trend are becoming, how to say, change it to achieve the 3D pose estimation from the RGB image rather than the depth image. And also RGB, from the RGB image, it is becoming, it is harder than achieving for achieving the 3D pose estimation, because RGB, there's no Z component, which means RGB image, they don't have any depth information. So mapping RGB to 3D pose is more challenging. Okay, so that is regarded as more harder problems compared to depth-based 3D pose estimation. Anyways, previously, early 2010s, depth-based approaches prevailed, but later, the RGB-based pose estimation is, becoming popular because they are ubiquitous and more challenging. And the other trend is they are becoming estimating the meshes rather than the skeletons. And later, thanks to the deep learning, this type of single hand pose estimation is becoming matured. So deep learning works very well actually for this type of one single hand pose. And especially in this domain, we are assuming that hand detection is completely done. So we are using ground truth bounding boxes. We do pre-processing before doing this 3D hand pose estimation. Okay. Because of that, their performance is becoming saturated. So later, in early 2020s, people are dealing with this type of more advanced scenario for the hand pose estimation that is having hand-object interactions. So the challenge here is when interacting with object, hands are occluded by the object. Okay, they're introduced some occlusions. Okay, so in the year of 2020, we developed this type of pipeline, actually wanting to reduce the gap between this type of hand-object interaction RGB images and single hand images. So, collecting data set for this type of domain is very difficult, okay? Especially collection of 3D pose data, their ground truth is very hard. So collecting data set for this hand-object interaction domain is very challenging, but there are already many data set available for single hand domain. So our idea is using the generative AI, using GAN, we are wanting to translate this RGB image into single hand image, okay? And then apply hand pose estimator, single hand pose estimator on these translated images. So that's high level idea of ours. So here X is the RGB image, and we wanting to first translate it into hand-only images using the GAN approach, one of the generative AI, and then achieve the single hand pose estimation. That was the idea here. And another stream of research was doing the hand pose estimation for interacting hand. So for example, single hand pose estimation, the model trained using the single hand pose benchmarks that is not generalizable to achieving the successful hand pose estimation in this type of images. So additional data set and additional models have to be developed for these scenarios. And this is the work we have done in the year of 2021, developing some end-to-end detection and pose estimation of two interacting hands. So in this paper, we want to achieve hand pose estimation for interacting classes and also for the single hand classes. And the idea, the pipeline looks like this. So here we have the hand detection network, which is the faster RCNN. So we attach faster RCNN here and fine-tune this faster RCNN using the hand data. But the idea is here you can see green box is meaning the left hand box, right hand is meaning the blue hand box. Okay. But red box is meaning interacting hand classes. So, I mean, when two hands are closely interacting with, sometimes detecting left-hand box, right-hand box separately is not helpful for further post-estimation process. Are you guys understanding this? 이해되나요? So if we wanted to capture left hand, right hand separately in this type of closely interacting hand, I mean, having this type of right hand box is not helpful for achieving the pose estimation. So here the motivation is having the interacting classes. We manipulate the ground truth of the hand box, and if their IOU of left hand, right hands are very close, we define it as the one box interacting hand classes. So we train this faster CNN to estimate three classes: left hand, right hand, and interacting hand class. Okay. And then for the separate hand cases, we apply single hand pose estimator. So that's streamed here. And here we apply interacting hand pose estimator if interacting classes are observed. Okay. So we apply different mechanism afterwards for the pose estimation. That was actually the contribution of this work. And nowadays, the research trends are again changed, and people are more becoming to dealing with two-hand and object interaction cases. Okay, there are many data sets proposed in this scenario, and this is actually the demo of our CVPR 23 work, which is called as H2OTR. Because there are two hand and one object, we call that as, there are some data set whose name is H2O, and we made some transformer-based architecture to deal with this problem. So transformer-based unified some architecture for understanding this scenario. That was our contribution. So we involved the DETR like transformer-based architecture by manipulating the output part. So DETR is object detection pipeline. So they somehow estimate the object classes and their locations. But here we are estimating two-hand, their pose, and object box and their probability, their class probability. So this is head is somehow different. And also by combining multiple frames estimated result. So this is the video. This is the one frame. For each frame, we apply DTR to estimate pose of the hand and object. And then combining those information temporally, we use another transformer to estimate their interaction classes. So this video, from the video, we frame wisely estimate their pose of hand pose and object pose, and then concatenating them, applying another VIT, and estimate their interaction classes. For example, here they are applying lotions. Okay, so this is very simple architecture, but at that time CNN was prevailed. So we first make the transformer-based unified architecture for understanding this challenging problem. So that was our contribution. And so I will skip this. And we won the first place in ECCB hand pose estimation challenge. So first place in hand pose estimation and second place in hand interaction recognition task using the single pipeline. And this is some project result that is embedding our pose estimator in the glass device. Okay. So this is the demo from the glass device. Another. So the research trend is our lab is also doing the research for making this architecture efficient. Okay, so H2R, that is the transformer-based architecture, but we wanting to achieve that in the lightweight way. So maybe some of you are here, right? The authors Elkan is now leaving, but Sayem and Yalem is here. Okay, and compared to Cho et al., that is our work in CBPR 23. So this is the speed. Okay, so if you go this direction, it means it's faster. And if you go in this direction, it means it is becoming better in accuracy. So previous CVPR 23 work is located here. It is not real time and the accuracy is limited. But here we are making our pipeline real time and increasing the accuracy. Okay. And here we extract some of the hand-related information in the encoder side. And this work is basically reducing the time complexity of the transformer. So, and transformer is composed of encoder and decoder architecture. So, and we actually removed the transformer encoder, replace that part using the CNN-based architecture because of the time complexity. And also, we add few more information to the decoder input. So we call that the transformers input, we call that as query. So we use additional information when constituting the query, hand-related information we additionally provide. And also we reduce the number of queries. So our motivation is because we are giving more abundant information, hand-related information for each query. So previous CVPR 23, they are having 300 queries, which means 300 input for this decoder. But now we greatly reduce the number of input to the decoder, but instead use more abundant hand-related information. So how to say, it is called as query optimized because we are optimizing these queries, reducing the query number instead combining more semantic features. So we optimize the query to reduce the overall time complexity. So that's the result. And this is the result of their pipeline. And another work was done by Jungwan. And actually, some of our group, our lab members are doing the 3D Gaussian splatting. And this work is actually doing the 3D Gaussian splatting from the monocular hand-object interaction videos. Okay, so this hand-object interaction video, we are building the 3D Gaussian splatting model for two hand and one object. And after building this 3D Gaussian splatting, we can re-render them into different viewpoint or different pose or different object. Okay. That's what this paper is wanting to achieve. One difference is for doing this type of thing, they first extract the meshes for each video and define the Gaussians for vertices of the model. So the hand here is we use for MANO model. And for these MANO vertices, we initialize the Gaussian and apply the Gaussian splatting optimization. So that's the big difference. So this is some quality visualization. So this is the previous work that does the similar thing using the NURF, but we did that using the 3D Gaussian splatting and also this EX avatar having, how to say, whole body models. But when we have the whole body model, it is not very optimal for this type of scenario. So we explicitly define the BX, which is the 3DGS model for this scenario, and it, showing far better result. And this is the thing I mentioned. So first, extract the meshes and define the Gaussian on the vertices of the meshes and do the 3DGS optimization. And we have some more contributions, but I will skip that. And in the middle, we can also improve the quality of the meshes. And this is the re-rendered, the 3DGS result. Okay, I will skip that. And last year, we won the first place again in the hands workshop, their challenges, okay, using this pipeline. And also, this is another work done in last 2 years ago already that generate hands, their sequences from the text input. Till now, I showed some applications that generate hand from the RGB image, but in this work, they generate hand motions from the text. Okay? So from text, pour milk with the right hand, this is the text description, and we are also inputting the object meshes. So for example, here we are giving milk, their object, their meshes. Then at the last, using the diffusion model, we map these two input signals to the sequences of the hand, okay? And then also refining them using the physical plausibility. So this is the actually, same as before. Previously, we map RGB information to the MANO, their parameters, but here we are mapping text and object signals to the MANO parameters. Okay. So we use the mean shape, but only estimate the pose sequences. And this is the demo result. So given this milk box and this prompt, this is the generated hand motions. And this is another, okay, I will skip that. And also, I introduce only the hand domains, but still body, they are also having skeletons And faces, they also have skeletons and their corresponding meshes. Body is also having SMPL, MANO, and this is flame or 3D MM. So hand, body, faces, they are defining the key point and meshes, and similar approaches can be applied to this domain. And there are many applications in this type of 3D pose estimation. So CCTV, we can monitor the crime and monitor the patient, or if the CCTV is attached in the car, we can control the car by increasing volumes of the sound by understanding the motions of the hand or others. And also, without remote controller, we can control the home applicant, okay, by understanding the human motions. These are some of the applications. And for the human, we did this type of things also. So HMR, the thing we have seen, only does the 3D mesh reconstruction for the single human cases. But for closely interacting human cases, the previous HMR suffers. So we developed some dedicated algorithm in ECCB 22. And also human bodies that is having clothes on the surface. So to be honest, the SMPL is not well representing the human surfaces. I mean, hand is always bare, so MANO is enough maybe, but human body, we are wearing the clothes. So human surfaces are, to be honest, different, a lot different from the SMPL surfaces. So in WSCB 24, we reconstruct the fine, detailed surfaces of the humans. And also, after revealing the 3D pose, we can map it to the 3D actions as well. So there are some work we have done for the action recognition. And using this 3D SMPL model, we did a lot of project as well. So from the KLRI, we get some data for train. And from the CCTV monitoring, we reveal the 3D pose of the human and detect whether humans are doing some abnormal actions or not. And for this CJ project, we submit this to the CVPR, and when the scenes are changed in the video, understanding that this person is same as the previous scene specific person, sometimes it is hard, okay? And also, anyways, that, I mean, understanding the 3D meshes in the drama, which has many multi-shots, are not trivial. So we dealt with that with CJ before. And also with the Hyundai Motors, we did this type of project to monitoring the human motions, especially for the safety to prevent some accident. And this is another project we did for the CCTV monitoring. And we did it for some of the things for the facial expression recognition. I will skip that. And we make some deepfake by understanding the 3D meshes of the face. We do generate some deepfake and also do some deepfake detection with Jumang University. And we also do some vision-based deep learning project as well. So this is the last slide of this tutorial. So any questions from your side? 질문 없나요? 마지막에 다 이해가 됐는지 모르겠네. 그렇죠.